Here's another video to the lecture Intro PDE. In this video we present the last section of chapter 4. So we finish with the heat equation. And finally we determine the heat equation of an interval and also of Cartesian products of intervals. So this should remind you to the determination of Green's functions on all balls. Here, instead of the balls, we determine the heat kernel on the Cartesian products of intervals. But we finally get a similar conclusion, namely that all solutions of the heat equation are smooth, and with respect to x, even analytic. Okay, so let's do the we follow the same procedure as in the last section. Yeah, the last section where we determined the heat kernel on the circle should be considered as a preparation for this section. Now we consider an interval, the interval 0, 0, 1, and we have again the square of d by dx minus, but with Dirichlet boundary conditions. Yeah, boundary conditions. So this means this should vanish, the eigenfunctions vanish at 0. Yeah? At 0, at 1. Yeah? The boundary of this interval is of course the set of the points 0 and 1. And there the eigenfunctions should vanish. And the claim is that we have the following eigenfunction: square root of sine of kx. This is with k in the natural numbers. They clearly vanish, yeah, at pi is missing, yeah, pi x, yes, since sine vanishes at all in multiples of pi, so this clearly vanishes at the boundary. And if we take twice the derivative, then we get eigenvalue, also minus d by dx square of 2. This is minus d by dx of pi k square root of 2 times cosine of k pi x, and this is pi square k square square root of 2 sine of k pi x. So eigenvalue is pi square minus pi, also this operator has the eigenvalue pi square k square. Yeah, and they form an orthogonal system. Yeah, here we calculate 0, 1, square root of 2 sine of k pi x times square root of 2 sine of k prime pi x dx. Okay, so what we get. And now we decompose. Yeah, this is of course 2 times. Now we use the addition formula. Yeah, and by the addition formula, this is just 0 to 1 of cosine k minus k prime pi x minus cosine k plus k prime pi x dx. Okay, and okay, now we know we have antiderivatives. Yeah, and then the antiderivative, also here, the cosine has the antiderivative is sine k minus k prime pi x, of course divided by pi times k minus k prime, yeah, for k not equal to k prime. And here we have from 0 to 1 and minus sine of k plus k prime pi x divided by pi times k plus k prime, also from 0 to 1. Okay, and if this is not equal, then in both cases we get 0, since these are periodic. Since this vanishes, yeah, this vanishes, so we get 0. Yeah, but for chi equals k prime, for this term we again get 0, but this term, by the cosine, if chi, then this is 1, we just get 1. Yeah, and this is 1. Also for k equals k prime, we get 1. Yeah, by this integral of this term, because then this is 1, and so we get 1. So we indeed have this. So this is really an orthogonal system. Now we want to prove that it is an orthogonal basis, an orthonormal basis. Yeah, so we want to prove that this is an orthonormal basis. Okay. So we prove now that this is an orthonormal basis. And for this we introduce the space A. A is a subspace of L2 functions with period 2 set. Yeah, and we continue, also what we do, we have 0, 1, 0. Yeah, and then, okay, here we just continue this function by reflection. Here we reflect here and we reflect here. So let me explain. If we have such a function, then we reflect here and here, and then we continue it periodically. Yeah, this is just an explanation. So reflect and reflect here. Yeah, and then continue and so on. And then we get periodic with period 2. Periodic with period 2. And the function is always antisymmetric and or odd function and odd. So this means f minus x is equal to minus fx. Yeah, this here by this definition, this subspace, you see if we insert 1, yeah, then you see it's really odd. And f von 1 plus x is if you insert minus 1. X minus f1 x minus 1 is minus f1 1 minus x. So yeah, there you see it's odd. Also here we get a negative, and then since we continue periodically, it's totally an odd function. So this space contains all odd functions with period 2. And if we write this in this form here, again, like in the last section, then we see we have the condition that a minus k should be equal to ak. Yeah, so we get so we get exponential 2 pi I kx minus 2 pi I minus 2 pi I kx, yeah, and this is, as you know, this is 2 times sine of kx. Okay, so for this reason, these functions here, they form the linear combinations of these functions. They form a closed subspace here. They form a dense subspace. They are dense in this space. And since by this map here, we have we may identify this space with this space. So altogether, we get that these functions here, square root of 2 sine of kx, they are an orthonormal basis of L2 of 0, 1. Yeah, okay. Here later I write this again as an exercise. I give an exercise, and in this exercise, yeah, you should fill in maybe some details. Yeah, but in principle, the solution is described here. Okay, and then again we have now this function, and then we can do the same procedure. Yeah, we can now do the same procedure. So we may, for all h, we have h is just equal to h of x is equal to k now in the natural numbers, ak square root of 2 sine of kx, with ak is equal to integral from 0 to 1 square root of 2 sine of ky h of y dy. Okay, and now we may again, yes, so in this way we now decomposed every function h, yeah, so for all h in L2 of 0, 1. So we have decomposed every function as a linear combination of eigenfunctions of the Laplacian with Dirichlet boundary conditions. And now we can write again the heat kernel. So what is now the heat kernel? Yeah, then the heat kernel is so the solution. Yeah. Now we may write the solution, and this is sum k in the natural numbers. So here we get the product. So we have now the integral over 1 exponential minus pi square t, and then we have sine of kx factor 2 sine of ky h of y dy. Yeah, so this is of course now integral from 0 to 1 h, so the heat kernel of x, y, t, h of y dy. Yeah, and so the heat kernel of 0, 1 now is just given by the sum k in the natural numbers without 0 to exponential minus p squared. There's a k missing here. K squared t minus p squared. No. Sorry, no pi. No, we don't have a pi. Minus k squared t sine of no, there is missing. Sorry. Yeah, of course, there's missing a pi. So we have here the pi. And sorry, here is missing a pi. I correct this. Okay, I have corrected here. There are missing pi's, and of course here in our notes there are also missing pi's. Yeah, all here we need a pi. Pi. Here is missing a pi. Okay, and here is missing a pi. And then here is missing a pi, and here is missing a pi. And then we get here minus pi squared sine of k pi x sine of k pi y. Yeah, so this is now our heat kernel. Yeah, so we have in fact determined the heat kernel. Yeah, and as we have seen, this sum solves. Yeah, we have constructed it that it solves the heat equation. Yeah, because it's a linear combination of eigenfunctions with the correct dependence on t. Yeah, here this is exponential of minus eigenvalue times t. Yeah, this is the eigenvalue. Okay, and so this is exactly of this form, and it clearly vanishes at the boundary. Yeah, this one sees immediately. So this is really the heat kernel. Now again, we may write this, yeah, by the addition formula. We may write this as exponential of minus p squared k squared t times cosine of k pi times x minus y minus cosine of k pi. No, maybe I write it. Maybe I write it. I need more space. So this is sum k in the natural numbers exponential minus pi square k square t cosine of p times k times x minus y minus cosine of k pi times x plus y. Okay, and then here we need a bracket, and then one sees this is again 1/2 of the theta function of x minus y half pi it, yeah, because here we don't have a 2 pi as before, and minus 1/2 theta function of x plus y half pi t. So we have really calculated the heat kernel of the interval. Now here in the exercise I explain a slightly different approach, but I also introduced this space A, and then you can check this. Now comes a very nice feature, that the heat kernel of a product we can just calculate by the heat kernel of the corresponding domains. So if we have two domains, omega and omega prime, of Rm and Rn, then we have the following formula for the heat kernel of the Cartesian product here. And so why this follows? This is a combination of the following results. First of all, in Rm cross Rn, the Laplacian is the sum of the Laplacian of, maybe I write it in this form. The Laplacian of Rm cross Rn is the same as the Laplacian of the first components plus the Laplacian of the second component. This is clear, because we have to take the sum of all of the squares of all partial derivatives. Then we take first the partial derivatives of the first components and then the second, and then this is clear. Okay, now the boundary of a Cartesian product. This is just the boundary of omega times this, and the union with omega times boundary of omega prime. Maybe I draw a picture to explain this. If we have an interval and an interval, then so here this is omega and this is omega prime. This is here the boundary of omega. This contains these 2 points here, and here these are the points of the boundary of omega prime. So we have for the boundary, we have two things. We have this and this, and we have this and this part. This part here, the yellow, the red part, so this is the boundary of d omega cross omega prime. And the yellow part is omega cross d omega prime. It's hard to read. Okay, this is the yellow part. Here. There we take. Okay, so this, I hope this picture helped to explain this formula. And now this is the second ingredient, and the last ingredient is for the fundamental solution. For the fundamental solution we have just that the fundamental solution is, so the fundamental solution of Rm cross Rn of x and t, this is nothing else as the fundamental solution of Rm cross, no, here I have need, of course, an x prime t. This is xt times phi of Rn of x prime t. Yeah, and if we apply the Laplacian, if we apply the derivative, yeah, d by dt by Leibniz rule, yeah, by the Leibniz rule, we get first this derivative times this, and then vice versa. Yeah, but since the Laplacian from Rm cross Rm prime n is the sum of the Laplacians, yeah, and this Laplacian only acts on this part, and this Laplacian only acts in this part. So this really solves heat equation. Yeah? This solves heat equation, and by this formula we see that it also obeys the other condition. Yeah? So these two properties now, also the Leibniz rule, this formula now proves this claim. Yeah? Now we see that, so omega of x prime t, y prime t just equal to the product times has both properties. Yeah, on the boundary either this or this vanishes. Yeah, we have this two boundary components. On this boundary, the first factor vanishes, on the second part, the second factor vanishes. Yeah? So it vanishes on the whole boundary, and it obeys the heat equation, yeah, by this Leibniz rule and this formula. Okay, so this is really the heat kernel of the Cartesian product. Now, what does this mean? Yeah. So this means we have now a nice formula for the n-fold Cartesian product. Yeah. We now have, this is product I to 1 to n h01 of xi yi t. This follows. Okay, there is a problem. 01 n has the boundary. Yeah? The boundary is not a C1 submanifold of n. Yeah? In fact, let me draw the picture. Sorry. This is the so here we have x and here we have y, and then you see this points, at this points we have no tangent space, yeah, to the boundary. So here we have no tangent space. So it's not differentiable. So it doesn't obey the condition that's a C1 manifold. Yeah, here no tangent space at these corners. Yeah, at the corners we don't have tangent space. So it's not. But so our proof of the divergence theorem doesn't apply. Does not apply. But one can, however, the divergence theorem holds for these domains, for omega, yeah, or more general for Cartesian products of intervals. A proof is given in the lecture partial differential equations. Okay, and now it's easy, yeah, to write, not only to write down for this, but now by the transformation, yeah, if we remember that the heat kernel, the fundamental solution, yeah, if we rescale it in this way, yeah, then only the prefactor changes. Yeah, so we have this property here. We have this property, and this behavior with respect to rescaling. Yeah, the only thing here, this combination doesn't change the exponent. The exponent doesn't depend on r. Yeah, because it's yeah, x minus y divided by 4 times t squared. So the r's in the top and the bottom, they cancel. So it's only the prefactor which only depends on the t, but it's in the bottom term t to the power of n half. So we get this factor here. Yeah, so we get this factor. Okay, and then we see we have for the heat kernel of this interval. So by rescaling we get this, and so in this way now we may write a similar formula than the formula for the Poisson representation formula. Yeah, now we obtain really this formula, yeah, for any solution of the homogeneous heat equation. We have this formula here now. Yeah, so if we know the values on the boundary of any of such a thing, yeah, then we now have this formula. Yeah, this follows now from our general formulas for the heat equation, and also for the heat kernel. Yeah, we derived this formula for the heat kernel, and this formula has now a nice consequence. Yeah, since these heat kernels we expressed as by the theta functions, and the theta functions are analytic. Theta is analytic on the domain x depends analytically on x as a for non-zero tau. Yes. Okay, there is a problem if the t goes to 0, then it's non-analytic. Yeah, so the heat kernel of x, y, t is analytic for t larger than 0. Okay, and then in this way we now get that that every solution of the heat equation, every solution of a heat equation is smooth and is for fixed T analytic. Is smooth and for fixed T analytic. So we have again a very similar result like for the Laplace equation. It's slightly weaker, because the dependence on T is not as good as for the Green's functions. Okay, so by this we close this section, this chapter 4 on the heat equation. So let's recall what we have done today. After calculating in the last section the heat kernel of the circle, we now used these considerations and calculated the heat kernel of the interval. Then we proved that the heat kernel of a Cartesian product is just the product of the heat kernels, if you insert the variables in the proper way. And then we obtained finally an analog of Poisson's representation formula. So any solution of the heat kernel on the parabolic cylinder of such a Cartesian product is completely determined by the values on the parabolic boundary. And this implies that every solution of the heat equation, of the homogeneous heat equation, is in the interior of the domain smooth and depends analytically on X. So thank you.